Assalamualaikum everyone. Today we are here for our digital logic and circuit assignments presentation, and our course instructor is Nafiz Ahmed Chisti. And according to the first question, we have come on the topic as the we have to use 8 to 3-bit encoder. Before that, my ID is 245600171. So that synchronizingly A, B, C, D, E, F, G, and H. Then cards will be space will be 6, and this binary digit will be 110, and digit 6 means this is to 8 to 3 encoder. What I have told you earlier. That means 8 input and 3 output. Here we can see the diagram, 8 to 3-bit encoder. And then the sensor diagram is the first. The sensor will be started, and then up down counter. From that, entry cards and exit cards also be counted. After that, 3-bit counters, then compare count max 7, and full display space available. Then the flowchart diagram, first it will start initialize counter to 0, then it will check entry sensor, further then it will check exit sensors, and further then it will check update car count up to 6, and then if the car count is equal 6, then it will display full, or not, then it will blink space available. And after doing all this, it will repeat it the word. Okay, then we have to uh, come down to the count diagram. ID parking capacity is 6. As we have mentioned earlier, we need to use max 6 car using 3-bit counter. Entry sensor is up and exit sensor is down. We have assumed it. And the cycle is 0040, 001 for 1, 010 for 2, 011 for 3, 100 for 4, 101 for 5, 110 for 6. And then we have taken JK flip-flop, and the JK flip-flop transition table is Q1, Q0, J and K. If the Q1 is 0 and Q0 is 0, then the J will be 0 and K will be don't care. And Q1 is 0 and Q0 is 1, then the J will be 1 and K will be don't care. And the Q1 is 1 and Q0 is 0, then J will be don't care and K will be 1. And if Q1 is 1 and Q0 is also 1, then the J will be don't care and K will be 0. For this transition, we need a transition table. And the first one is present state, second one is next state. And as we have mentioned the earlier here, the entry sensor up is 1 and exit sensor down is 0. And then we have assumed that this M will be up and M bar will be for down. Then present state, Q2, Q1 and Q0, 3-bit. And the next state, if for up, the next state will be Q2, Q1 and Q0, and for down also Q2, Q1 and Q0. And the first state, if the present state is 000, then the up state will be 001. And for that, if the present state is 000, the down state will be 111. Let's go to the diagram for as explain this. 000, for if the M is up, it means if that is 1, then it will go down to 001. And if that is M is not 1, which means M is 0, that means M bar, then it will go to back. Back means down, that is 110. Okay, then for Y, and for the value of Y, we have assumed the table for JK flip-flop for K map, and from that we have grouping. For J0 we have assumed 3 groups. For that we have obtained J0 is equal to Q0 bar M bar plus Q2 bar plus Q1 bar, and K0 is 1 because we have assumed the K naught whole will be in one group. Whole K naught, 16 cells will be in one group. That's why we have assumed K naught. And for J naught, we have assumed two groups. After that, we have obtained J1 is equals to Q naught bar M bar plus Q naught M. Also that Q naught. And for K1, we have assumed three groups G1, G2, G3, Q naught bar M bar plus Q naught M plus Q2 plus Q naught bar M. And for J naught, sir, J2, we have assumed two group. After that, we are obtaining Q1 bar, Q naught bar, M bar plus Q1 plus Q naught M. And for K2, we have also assumed three groups. For that, we have obtained K2 equal to Q2, Q1 plus Q1, Q2, Q naught bar, M bar plus Q1, Q naught bar, M. Okay, the circuit will be of synchronized circuit. For that, the clock will be in from same base. Okay, the every bit clock will be from same base, and here three registers are used to hold the binary value that cure SIPO register. First of all, we need to understand SIPO. What is SIPO? SIPO is synchronized in, parallel out. Here the data is in the SIPO is serial in, parallel out. Sorry for my mistake. And the data is in serially, and it is out in parallelly. That Q0 and Q1 is being out parallelly. Now a 3-bit comparator is used to compare the value of A and B. A will come from the registers that are connected to the encoder, and B will be initially 0. The up-down counter is connected to a parallel in or out register PIPO. And what is the PIPO means? PIPO means parallel in and parallel out to hold the counter value. Okay, there's the diagram of a PIPO. That is, it's coming from D0 is coming from parallelly, D1 coming from parallelly, D2 also coming from parallelly, and the output Q0, Q1, Q2 is also outing parallelly. And further then, we have forward to our next question, question 2, which is parameter calculation of space available, and the P is A plus B plus D plus E plus G into 2, and we have obtained A plus B plus D plus further that is come from my ID, which is 2 plus 4 plus 6 plus 7 plus 8 into 2 equal 54. And here in my ID, E is equal to 0. That's why we have replaced by E A plus B plus H, which is 7. Then that D will be 100 minus P is equal to 46%. And the frequency F is A plus C plus 5, which is 12 Hertz. Capacitor equal to 50. We know that duty cycle D is equals to T of H divided by T of H plus T of L. And the T is equals to T of H plus T of L, which is 1 by F. Also, we have determined that F is equals to 12. Then 1 by 12 equal to 0.08 seconds. Then D equal to TH by T. Then TH equal to T into D equal 0.08 into 0.46, 0.0368 seconds, 36.8 milliseconds. Then TL equal to 0.08 minus 0.0368 equal to 0.0432, which means 43.2 milliseconds. Then the register R2 equal to, for R2 we have to calculation TL equal to 0.693 R2 into C1. That means R2 equal TL divided by 0.693 into 50, which means 1.247 kilo ohm. The value of R1, TH equal to 0.693 R1 plus R2 into C1. C1 means capacitor 1. Then R1 is TH by 0.693 into C1 minus R2, which is, for that calculation, we have obtained to the conclusion that it is 0.185 kilo ohm. Then we need the 555 timer. That's why we have obtained the R1 here, R12, capacitor 150, then capacitor 2 0.01, and 555 timer reset and VCC. Here a stable 555 timer will blink where there will be space available, which means a stable 555 timer will blink when there is a space available for car. Okay, then another circuit we know T for W is 1.1, R1 C1. Then from that equation we have come to the conclusion R1 will be 2.02020 kilo ohm. For that we have again taken the 555 timer, and this is for monostable. Okay, then here is the 555 timer, 1 resistors, and here monostable 555 timer is used for the showing of full display, and it will show the full display. And from that our question part 2 is finished, and the third question is we get from section 2 is T of H equal to 36.8, which is greater than 4 millis, and T of L equal to 43.2 is also greater than 4, and T equal to 1 millisecond. Okay, T of H equal to 4 and TL equal to 4. TH equal, assume that A0, A1, A2, A3, and TL equal to B0, B1, and B2. The state diagram is 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0. Synchronizingly, we will assume that it will be in A0, A1, A2, A3, B0, B1, and B2. And for that FSM, we have draw the circuit here, and the next state logic, output logic, present state logic, and the clock will be input in the present state logic, and it will also in the reset will be connected with present state register. Okay, then this is the one of the important table in this part, that if that reset is active, then the present state will be don't care, input will be don't care, and next state will be A0, which is 0, 0, 0, and the function will be in ready position. That's why we have assumed here as 1. And after the system is running, then we don't have to check the about reset. Then we will continue to further, that is present state, input. Also we don't have to bother about input, because it will be don't care. Okay, then because it why it will be don't care, because the whole system is ongoing, on process. Okay, then the next state will be A0. That's why the next state become the present state, which is A0 000, and as I have said earlier, input will be don't care, and the next state will be 001. And then further, then if, because it's A1 and we have assumed that A1, then A1 will be 1 because it's activated there. And from the diagram, as you can see that the 001, 010, 011, if the A1 is the present state, then A2 will be the next state. That the next state will be the present state. After that, like this, then A2 will be the present state, like 010 will be the present state, and then A3 will be the next state, like 011, and after that A3 will be the present state, and B0 will be the next state. Let's see this, that A2 is the present state 010, then A3 is the next state, as I have told and mentioned in the diagram, and then A3 will be the present state 011, and then B0 will be in present state, like 100. Okay, then here we have come to the next state equation, ns0, ns1, ns2. You have become a question, you have a question, right, that what is ns0, ns1, ns2? As I've said, it's a next state equation. And how we have obtained it? We have obtained it by, we have to check every next state for ns0. For ns0, which bit has 1, like A1, in A1 the ns0 bit has 1, then in A2 ns0 bit has 0. So we will not take ns0, we will not take A2. Okay, then A3, in NA3 the ns0 value is also 1, then B0 is 100, then ns0 value is 0. We will not take B0. Gradually, sequentially, we will take like this, because in this ns0, for this ns0 we have to compare with present state, PS2, POS1, and PS0. Okay, then for ns0 A1, we have to check. Why we have to take A1? Because that's 1. ns not at 1, we have to check the present state. The present state 3 value is 0 0 0. That means for this 3 bit, everyone will be in bar, like ps not bar, ps1 bar, ps2 bar. Okay, like this, ps1 bar, ps2 bar, ps not bar. Gradually, if we come to a second, that is 0 1 1. Okay, then that's we have got 1 ns not activated. Then we have got to present state. For this present state, what is we are seeing? We are seeing 0 1 0. For that, what is 0 0 means ps2 bar. What is 1? That is ps1. And next is ps not is 0. That means ps not bar. Okay, then let's not assume, we can say that the ps2 bar, ps1 and ps not bar. And we have multiplied reset bar. Why we have multiplied reset bar? Because for that one reset, the system will continue and we can go into the system. Then if the further is 0, for the system reset is 0, we will not care about that, because also because we have also into the system. That's why also we have to multiply the reset, because the reset value is 0. That's why we have to use reset bar. That's why we have used reset bar. Then also the output state a and b, in which segment we have got a is we have got 1 for output and we have got 1 for b. Then we have also go to the present state. Remember one thing, where we will getting 1, we will go to in present state, and from present state we can make equation. We will not look into next state. Remember, we will also see in present state. Okay, from that we have got it, a equal to this equation and b equal to this equation. Okay, then there is a system Verilog code for this module TLC. It's your choice what name will be given. Input wire clock reset, output wire ready AB, and the range is 2:0 is P state for present state, and wire 2:0 equal n next state. Assign n state 0. This we have written n state 0, n state 1, n state 2. From where we have written? We have written from this equation, ns0, ns1, ns2. We have written from this equation. And also remember, in this case, always you have to remember that always at the rate pose as clock. What's pose as clock? It's positive edge of clock. When the positive edge clock is starting, then our code, then our system will be running. Okay, then p state 0 is less equal n state 0. You can, if you don't remember this, you can memorize this also. Okay, then it will help the in exam. Okay, then assign a, what we have got from a and what we have got from b, like this, n state 1, n state 2. We have also mentioned it there. Okay, in the question 4, there is some limitation in our project of this or assignment or whatever we are saying in practically designing. In part 1 and 2 has some limitations. What are the limitations? First we can say that 1, a counter size. The 3-bit counter is different for 7 cars or 6 cars, what we are saying. Then the time procedure is the 555 timer may not provide exact 46% duty cycle with standard registers. Okay, and the third one is display complexity. 7-segment display or 6-segment display requires complex wiring for full and space available. Fixed capacity. System cannot dynamically adjust for changing parking capacity. We made some modification, and for that reason we made some modification. If we don't want to face that problem,